All right, so this is a very good survey, a survey of quantized graph representation learning, connecting graph structures with large language models. This paper in 2025 from Singapore. Recent years have witnessed rapid advances in graph representation learning, with the continuous embedding approach emerging as a dominant paradigm. However, such methods encounter issues regarding parameter efficiency, interpretability, and robustness. Thus, quantized graph representation learning has recently gained increased interest, which represents the graph structure with discrete codes instead of conventional continuous embedding. Given its analogous representation to natural language, QGR also possesses the capability to seamlessly integrate graph structures with large language models. As this emerging paradigm is still in its infancy, yet holds significant promise, we undertake this thorough survey to promote its rapid future prosperity. We first present the background of the general quantization methods and their merits. Moreover, we provide an in-depth demonstration of current QGR studies from the perspectives of quantized strategies, training objectives, distinctive designs, knowledge graph quantization applications. You see, on A is just a continuous graph representation that most of the papers, maybe 95%, are in this area. It's a continuous representation. But at the second, the B, is the quantized graph representation, which represents the graph structure with discrete codes instead of conventional continuous embedding. In real life, discrete features are often preferred for representation. For example, male, female, place of residence. So based on this intuition, quantized representation came into being, which is not a hot topic in the computer vision domain, that can facilitate image generation by combining with transformer or LLMs. So it's now, even in computer vision, they have combined the image generation, they combine it with transformer or LLMs. So it has some merits. Explainability, interpretability, robustness, and generalization, embedding parameter efficiency. So these are the advantages if we use QGR. Seamless integration with NLP models and so on. The mainstream quantization methods can be roughly categorized into product quantization, vector quantization, finite scale quantization, and anchor selection and assignment. For example, product quantization. The core idea of product quantization that goes back to 2011 is to divide a high-dimensional space into multiple low-dimensional subspaces and then quantize them. The idea of vector quantization is that to effectively learn quantized representation, the core idea involves assigning the learned continuous representation to the codebook's index and employing the straight-through estimator for effective optimization. So the formulation is that we have f of e, f of d, f of reconstruction factor. So x hat is the reconstruction feature after quantization is performed. So after you did x hat, and f of e, as the name suggests, is encoder. D name suggests is decoder. And Q is quantization. So first quantization, then we give it to the decoder. So the residual vector quantization algorithm is as follows. Once you have given the encoder as an input and the code representation C, this C is the input, then your output is the quantized representation. So we get your residual, and then you add f of residual to Q, but you reduce the residual by f of Q. So the VQ strategy yields a nearest neighbor lookup between latent representation and prototype vectors in the codebook, indicating that the node I, for example, this one, is assigned to code for C sub m. Therefore, the model can be optimized by a straight-through estimator. So this SG, it means stop gradient, and we have finite scalar quantization. Because of introduction of the codebook, there would be complex technique designs and codebook collapse. So FSQ projects the hidden representations into a few dimensions, usually less than 10. And each dimension is quantized into a limited selection of predetermined values, which inherently formulates a codebook as a result of these set combinations. So the process of rounding simply adjusts a scalar to its nearest integer. So we have this loss. There are quantized graph learning, there are quantized strategies. For example, between GCN layers, interlayer residue is carried out to enhance representation. So C here is the quantized one, quantized latent variable. So the training can be either at node level and it could be at edge level like this, and it could be at graph level. For the graph level, they have used these laws modeling relationship between graph pairs. So the architecture is very easy to understand. This is first we give it the graph to the general encoder. Then here the codebook allows us to do quantization at this part. After that, you give it to the decoder, but you can use this for prediction at the node level, as I said, edge level, graph level. So at the node level, you have feature reconstruction. And at the edge level, you do link prediction. For the graph level, they use this objective of graph contrastive learning, invariant learning, or you can use DGI. For example, this is how we give it to the LLM. Because once it is quantized, now you can give it to the LLM for the answer. For example, given a node, you need to classify it among case-based genetic algorithms, with the node's one hop information being a mass traverse handle, the second hop information being provable, revolution, creative, three hop information being hypothesis. The node should be classified as, so the output, for example, says rule learning. Given a triple knowledge graph, you need to present it to predict its validity based on triple itself and entities quantization. For example, a triple, a H, R, and T, the quantization is code of H. The quantization of T is code of T. Then please determine the validity of the triple. So this is how you integrate your LLM with these quantization, because once it is quantized, you can give it to the LLM with some instructions. Molecular task is very interesting. So has been used for molecule tasks and an AI for science scenarios, including molecule property prediction, which is both classification and regression, molecule text prediction, and protein and RNA reconstruction. So they integrated with LLM. This is the summary of cutting-edge studies for QGR learning. What is the quantization of each of these models? What is the training of them? What is the application of them? And what is the graph type?